All right, let's talk about one of the biggest, most fundamental rules in all of physics. But we're not just going to talk about what it is. We're going to ask a much, much deeper question. Why is it even a rule in the first place?
You've probably heard this a million times, right? The law of conservation of energy. It's an absolute bedrock of science. Everything from a chemical reaction to the explosion of a supernova has to follow this rule. The total amount of energy in the universe is fixed. That's it.
But have you ever really stopped to think about that? We just sort of accept it as a fact of life. But what is it that's actually enforcing this law everywhere, all the time? What makes it so that not a single speck of energy can just pop into existence or vanish without a trace?
Well, to even begin to answer that, we have to get a little weird. We're going to explore an idea called single point theory, or SPT, and it asks us to completely rethink what the universe even is.
So, here's the core idea of SPT. It says our universe isn't some static box where things happen. It's more like a movie, a process that's constantly being generated or refreshed frame by what's called a primary cycle.
And the speed of this refresh, it's just staggering. It happens at the Planck frequency. That's a number so big it's hard to even describe. We're talking more frames per second than there are grains of sand on all the beaches on Earth. But this brings up a huge problem.
Okay, wait a second. If reality is being powered by this constant cycle, doesn't that mean energy is being pumped into the system with every single one of those ticks? So how on earth can energy be conserved? It seems like a total contradiction.
The secret, SPT says, is that it all depends on how you're looking at it. There are two completely different ways to view the system: up close, at the microscopic level of a single frame, and from far away, at the macroscopic level of the movie that we actually experience. So at that super tiny microscopic level, the universe is what's called a driven system. Energy is constantly flowing in and out. But from our everyday macroscopic point of view, all of those incredibly fast fluctuations just get averaged out. They blend together into the smooth, continuous reality we're familiar with.
Okay, so what this is really saying is that down at that tiniest level, the Planck scale, energy isn't conserved in the way we think. Instead, there's a balance law. In any single tick of the clock, power is being injected and radiated away. The total energy is actually changing moment to moment.
Let's stick with that movie analogy. Imagine you could hit pause and look at a single frame of reality. What you'd see would be chaos, a crazy, flickering storm of energy being injected and zipping around.
But of course, we can't see just one frame. We experience trillions upon trillions of them every single second, and when you zoom out and let all those frames play together, something amazing happens. All that randomness, all that chaos, it just cancels itself out. A smooth, predictable story emerges.
And that is the punchline. When you take the average of all that injected power over time, it all balances out perfectly to zero. The law of conservation of energy just emerges. It's not some fundamental command written in stone. It's the stable average of a much deeper, chaotic process.
Okay, I know that's a lot to wrap your head around, so let's bring it back to Earth, or, well, back to a star. To make it more concrete, let's look at one of the most extreme events in the universe, nuclear fusion, and see how this idea holds up.
Deep inside our sun, the pressure is so immense that 4 protons get squeezed together. They fuse, and what comes out the other side is one helium nucleus and a whole lot of energy, as sunlight and heat.
But here's where things get weird, and this is something that puzzled scientists for a long time. If you could somehow weigh the 4 protons before they fuse, and then weigh the helium nucleus after, they don't add up. The final product is always a tiny bit lighter. Mass has literally vanished.
And this little bit of missing stuff, it's called the mass defect. Now, it hasn't just disappeared. It's been converted directly into that massive burst of energy that powers the star, and it follows Einstein's famous equation, E equals mc squared, perfectly. So how does single-point theory see this? Well, it says it's not about one thing, mass, magically turning into another thing, energy. Instead, it's about the underlying field itself changing its shape. The energy that was tied up in the proton pattern gets released as the field settles into a more stable, lower-energy helium pattern. The mass defect we measure is just the echo of that reconfiguration.
All right, let's pull all of this together. Where does this leave that unbreakable law we started with? Has SPT just smashed one of the core principles of physics? Well, no. Actually, it does the opposite.
The key thing to get here is that SPT doesn't throw energy conservation out the window. Not at all. What it does is give it a real physical foundation. It explains why the law works at our scale. It's not just some random rule of the universe. It's the predictable, statistical outcome of that deeper, more frantic reality.
It really changes how you think about it. It's not a static rule written down somewhere. It's more like the stable, beautiful harmony that rises out of a chaotic orchestra that's always playing. Conservation isn't silence. It's the sound of perfect balance.
And that's the big question this leaves us with, isn't it? If the law of conservation of energy is actually an emergent property, what other laws that we treat as absolute axioms are just the surface-level effects of a much simpler, more fundamental process driving everything from beneath?